I am the team leader of Workholding at Makino in Mason, Ohio. I'm one member of approximately 50 to 55 person team that works at Makino dedicated to turnkey and integration projects. So I'm going to go through a few examples of fixtures that we've used, designed in automated systems, give you an idea of some of the virtues that they extol. Reducing operations. On this particular fixture, you can clearly see that this is what we call a window fixture. What a window fixture is it allows us to machine on both the front side and the back side of this part. So we were able to machine this part in one operation. Why is that a big deal? Less part handling, only one process stream. No matter where the part came from, it's only gone through one operation, so there's only one process stream to follow for quality. Versatility and loading in this case, this particular part was going to be automated, but wasn't going to be automated for the first 6 months of production due to the lack of availability of the robots. So the customer had to get up in production, but in the meantime, he needed to hand load these parts, have operators load the parts. We were able to accomplish that in here by taking into account the fact that both a human being and a robot had to load this part. So it's built into the works of the fixture. We'll talk a little bit more about part retention and things of that nature as I go on. Built for automation. There's a lot of things I talk about in this presentation that are designed for created to be built for automation. But if I can give you guys one piece of advice, if you're going to have an automated fixture, you want to make sure that you're using double-acting hydraulics, okay? What is double-acting hydraulics? Double-acting hydraulics means that you clamp under hydraulic pressure, but you also unclamp under hydraulic pressure. In an automated system, you don't want to use single-acting clamps, which are advanced hydraulically and return with spring pressure. What happens over time, coolant is sticky, right? If it gets on a part of yours and it sits over the weekend, it can gum up the shaft or the shaft seal connection. And what eventually happens is a clamp won't fully return. It won't get out of the way. If you're hand loading, the operator he can just touch it with his fingers, knock them out of the way, grab the part, take it off, put a new part on. The robot can't do that. The robot's going to go in there, grab that part, try to pull it out, and if those clamps aren't returned, it's going to try to take the entire fixture with it. So double-acting hydraulics would be one suggestion under the built for automation category. I'll talk about more. Distortion reduction using sequence clamping. On this fixture, on the next slide, I'll tell you a really interesting story of how we were able to do that. And of course, this fixture was fully integrated with the FHU system. On this particular part, we had very small locating areas, very small pockets that we had to locate in. Again, we had to machine both sides of this part not at the same time, but in this one operation. So what we saw, these are 3,000 PSI capable clamps that are on the fixture. We saw that as we were clamping this part in those teeny tiny little areas, about less than 1/4 of an inch in diameter, if we applied anything more than 300 PSI of pressure on that clamp, it distorted the part just enough that we couldn't achieve the 30 microns flatness that we had to have on the back side of that part. All right, that's cool. We can adjust our FHU system down to 300 PSI. That's awesome. Well, those are 3,000 PSI clamps. The minimum operating pressure is 700 PSI. So we dialed it down to 300 PSI, and sometimes the clamps would clamp and sometimes they wouldn't because we were below the minimum operating pressure. So what did we do? We got a little creative. We put in a reducing system, an optional system that we put in there. We clamped the clamps at 1,500 PSI to make sure all the clamps clamped. We then dropped the pressure on that clamp line all the way down to 0. We didn't unclamp it, but we just dropped the hydraulic pressure down to 0. At 0 pressure, the part was able to relax back into its original shape. And then I could jack the pressure back up to the lower 300 PSI and clamp the part in place because the arm had already swung at 1,500 like I told you. And at 300 PSI, we were able to reclamp the part. That was enough force to hold the part in there when we machined it, and we were able to get the distortion out of the part. Now, if I didn't have the FHU, I'd be in a world of hurt. And this is an actual case scenario where we actually had to do this on the fly. So with the FHU, it allows you to be flexible. It allows you to get out of trouble that you've inadvertently gotten yourself into. In over 29 years, I've gotten myself into a lot of trouble. And it's a tool that can help me get out of it pretty quick. One more thing about differential pressures. We also had another case, not this particular fixture, but we had a case, multiple cases actually, where we needed to clamp a part at 3,000 PSI in order to take off the heavy amount of stock we needed to. But once we got through all that stock, and we had to have a tight either surface finish requirement or flatness requirement or a roundness requirement, we can, in the work zone, we can clamp at 3,000 PSI. We can actually unclamp the part, again, in the work zone, reclamp the part at a lower pressure to do finishing. So we clamp it at a higher pressure to do our roughing cuts, unclamp it and reclamp it, all in the work zone at a lower pressure, allowing us to do our finish cuts at a lower pressure to reduce the distortion. Again, another way FHU bailed us out of a situation we were in. This particular fixture as well had, the customer had a desire or need or want to probe his secondary and tertiary locators. The reason why he wanted to be able to do that is, as we all know, machine tools never get crashed. But he wanted the ability to, once a month, go in there and check the position of the part relative to the zero on the fixture to make sure that the part hadn't been crashed or the machine hadn't been crashed. And if it had been, if the part moved because of any number of different reasons, it could adjust the offset to where the part position is right now. Now, we also have, I'm working with a customer right now that has a cast iron part, and we're going to be machining a series of bores in line with the part. And the problem he's having, he currently makes his part on another set of machines. The problem he's having is the parting line goes right down through the center of that bore. So he's getting a lot of shift from one side of the casting flask to the other side of the casting flask. There's a lot of shift. So what happens is he sets it on his fixtures. His fixturing points are solid, they're good. But depending on which mold or which day or how much shift it got in there, he makes parts, he machines parts all the way through the process, only to find out when he takes them off, they're not cleaning up on part of the diameter. So what we're doing is we're using it, the fixturing in the same way, but we're using the machine probe, an option. We probe that cast bore on every part, and we offset the program based upon the data that we get from that probe to allow us to center on the shift where it is to give the machine tool the best opportunity to put that bore directly on center. Again, going back to this part here, thoughtful design. It's a nice way to put that. It's collaboratively done between the application engineers and the work holding team. We had to be able to not only hold that surface flat within 30 microns, there was a visual specification requirement. There was no step over allowed, even if you couldn't measure it. You can't take a small mill and buzz back and forth. If you can see a line between the tool paths, that was unacceptable to the OEM. So we had to create a fixture that allowed a mill to come in Z, walk all the way across that part in X, both keeping the tool off of it before and allowing the last tooth of the tool to come off. You'll notice that there's nothing protruding out of that fixture in the area where the red part is. Anything that protrudes it is above and below. And that created some challenges on the fixture with the way we're clamping. Those circles sticking out of there are the actual the back end of those cylinders. So we had to get creative there in order to make this a one operation process. This fixture here is another example of an automated fixture that we did. These kind of go through some fancy graphics here, highlighting all the different aspects that kind of went into it. Again, this is a window style fixture that allows us to access features in the back. So on this particular part, again, we have incorporated part loading guides. Now what is that? Basically what those are is it allows the part to be guided onto the locator. So even if you have automation that's bringing it in there, especially if the automation is grabbing on cast areas of the part, it's not always consistent. So we have load guides under that guide the part, direct it to where we want it to be. We want it to be in place where it needs to be, as close to it when the robot lets go of the part. In those load guides though, we also, if you notice, these parts are 180 degrees from each other, okay? It's the same part. The right-hand nest and the left-hand nest are 180 degrees from each other. There's two link clamps right in the middle between the two parts. This part was done on an A61NX. If we had the parts that in both the same attitude, one of those link clamps would have to be on the outside and one of the link clamps would be on the inside. If you look at the relative size of the tombstone to the pallet base, you notice that the tombstone is very wide. We had to do this in order to keep the fixture within the work zone of the A61NX. If we couldn't do that, we'd have to go to the A71NX, which would be a larger machine, more money, more floor space, etc. So creatively, we got that done by rotating the parts 180 degrees. But those load guides also as a pokey yoke. You can't, even though you look at the flanges of those parts, they are perfectly symmetrical, top to bottom and all around. So it'd be very easy for an operator to load it in upside down. It would go in there. But those load guides have pokey yokes built in there that will not allow them to be loaded incorrectly. Hydraulic actuated work support, we talked about that, the 3,000 PSI. Again, we had to employ that in the area. On the right-hand nest, you can see it about halfway up. There's a hydraulic work support under there. The two locators were too far apart from each other, and our cutting tool force bowed the part down there, so we had to add a hydraulic work support in that area. Hydraulic clamping on rest pads, of course, I mean, that's kind of what the meat and potatoes of hydraulic clamping is. I offer this suggestion for you as well. You always want to have that clamp directly over top of a locator. Anybody that works with product designers, you can let them know that if you cannot clamp over top of their locators, you're going to struggle. You're going to struggle making parts. Because if the clamp's not over top of the locator, you're going to bend the part, right? If I apply pressure directly over top of my locator through your part, I can't distort it. But if I have any type of a lever, no matter how far away I am from that clamp, I'm going to have a lever and it's going to want to pull or push that part around. So you want to clamp directly over top of those rest pads wherever you can. And as I mentioned, there is a window to allow access to features in the back, which was key in this case because the bores that you can see on the lower right-hand nest, there's bearing bores on the inside of that part, and on the 180-degree side, there's also bearing bores and seal bores. The concentricity between those parts, those features, if we had to do those on two operations, you would have two different setups. And that would create a tolerance stack and make it much more difficult to have a statistical capability. So being able to bore, index, and bore allowed us to achieve a higher quality. Prevent load failures. Well, that would be a good thing. Obviously, in an automated system, we want the robot to drop the part off and never to have a load failure. Well, a robot alone can't do that. So we employ air detect. Air detect would be those pneumatic lines I talked about on the rotary unions. I'll show you on the next slide what air detect looks like, but basically it is sending air through your rest pads that builds up a back pressure that we can read with a sensor to let us know whether the part has been seated or not. Part retention. We want that part when the robot drops it off, or a human for that matter, whoever loads the part, we want the part to be as close to the locators, if not sitting on the locators, as humanly possible. So we design part retention, spring-loaded devices. Now you can buy them commercially, but they're not very good. And I've yet to find a commercial retention device that can last in the environment that we put it in, the coolant, the chips, etc. So we design most of those, if not all of those, on our own. And the idea is that we use spring force to push the part against our locators. If you will, if you imagine yourself an operator, if you were a robot, you take the part, put it in the fixture, snap it into place. It wants to snap into place so it hits against all the locators. Ideally, when the clamps come in, we don't even want to see the part move because it's already on the locators. All the clamps are doing is adding holding force to where it's at. But that takes a little bit of work, and again, you're not going to find any of those in a catalog somewhere that you can buy that are worth a hooey. Clamp confirmation. We want to make sure in an automated system that our clamps are open when we want them open and closed when we want them closed. The way we do that with the FHU is we have pressure sensing. We can tell when the clamp pressure has been made on each and every circuit. We monitor each and every circuit individually. So we know when hydraulic pressure is made on the clamp side, we know when it's made on the unclamp side. Even if I had a seal failure inside the cylinder and was bleeding fluid over from the unclamp side to the clamp side, I would know that because I wouldn't make my pressure sensor. My pressure sensor would say, there's a fault here, I'm not getting up to the pressure I need. So I know that the cylinders are moving by monitoring the back pressure that we see. If you want to get into a what I like to call belt and suspender scenario, what you're looking at here on this screen, these two cylinders that are directly on top of each other, this is a bailiff inductive sensing system. So the bottom cylinder is permanently mounted to the machine itself. The top cylinder is mounted to the fixture itself. And there's a 1 millimeter gap between the two. What I can do is I can inductively send power. They do not connect, there's a gap. I can send power from the machine tool into my fixture with enough power that I can run 8 proximity switches on the inside of that fixture. So I can have dogs on my cylinders that physically move back and forth, and I can detect whether the clamp is closed or the clamp is open with proximity switches. So I then have physical confirmation that the cylinder has moved from position A to position B. We have very few customers that use it, but they insist on it. Most of our other customers, we use the pressure sensing. Another thing we can do with the air detect system is we can do broken pin detection. So you got the part seated up against the rest pads, everything's solid there, the clamps are engaged, everything's good, but yet you made a bad part. Well, how did that happen? When you put the part onto the locating pins, one of your locating pins was broken. Your diamond pin, let's say, was broken. So you're not getting that tertiary location, the rotation location. How many parts are you going to make before you discover that pin was broken? There's nothing on the machine to detect it, but we can put an air line or an air feed into those pins, have the pins be somewhat hollow, that if a pin breaks off, we will be able to detect that pin is broken by the loss of back pressure on that air. Once that pressure drops down below a certain level, it tells me there is a broken pin on this fixture somewhere. It needs service, it needs intervention, and we will not allow that fixture to pallet change into the machine to make bad parts. That's just another creative way you can use air detection. Rough load guides and poka yoke, we talked about that. All these types of things, all stacked on top of each other, is what I talk about built for automation, right? Building the fixture for automation so it's robust. Going back to the air detection, the rest pads, which you're looking at here, what we have is a rest pad that's sitting on a surface, and that is a 1 millimeter diameter hole that we squirt air out of, if you will. And as the part comes over top of it and is clamped, it seals off. It doesn't seal it off, right? I mean, especially on a cast part, the cast part has some, waviness to the surface. So it's not like you can seal it off and put soapy water on it and not get any bubbles. There's going to be air escaping from it. So again, we use a pressure differential switch to determine whether the part is clamped or not, or seated against the rest pad. When all the rest pads are open, you've got free-flowing air going through those 1 millimeter holes. There's a certain pressure threshold that we look at, okay? When we have a part that goes on there and we know there's no chips and it's solid, there's a certain back pressure that we see, the difference from the open to the closed. That's what we're looking for in these scenarios. So going along with this, you take a look at the size of that chip that's on a human finger there. So what are the potential costs of a chip on a locator? We use coolant nozzles with through fixture coolant in addition or in combination with those air detect locating points to blow through on the locators. If used properly, we can detect a 10,000th chip being on one locator. We are able to detect that there is a 10,000th gap between the rest pad and the part. Now, why did I say if used properly? We have some customers that want to put 12 or 15 parts up on a fixture. They want to use one airline to check 12 or 15 parts. You've got 3 rest pads per part, 36 to 45 rest pads. You're not going to get, with that many holes, with that many orifices, you can't detect a small chip, right? Again, you're looking for a pressure differential. So if you've got 36 orifices with that air flowing through, you're not going to be able to detect as fine a chip as you could by having one airline per set of pads, okay? So you look at it, it's a positive, but you have to be careful how you use it. You can't have too many lines, too many points, rest pad points on each pneumatic line. And of course, it depends on whether the part is as cast that you're sitting on or if it's a machine surface that you're sitting on. Chip shedding, another thing that we can't stress enough. The ability, you must get chips off the fixture in an automated system. You don't want chips on rest pads. You don't want chips on locating pins. In this picture here, those 2 flaps that stand out there, they're really not chip sheds. This is a motorcycle crankcase, and it's very visible to the customer, the end user, or the purchaser of the vehicle. They didn't want, it's a painted part, it's a powder coated part. So in order to keep the chips on the top part from bead blasting the part below and creating a non-perfect surface on the part below, this is the same fixture. I want you to notice from a chip shedding standpoint, on the areas of the part where the part is located, upper and lower, you notice there's not a single horizontal surface anywhere. Everything's got an angle to it or it's round. The idea behind that is when chips hit it and coolant hits it, it rolls down off that face. A horizontal flat surface will allow chips to gather. Another thing we always want to see on automated fixtures, we like to do this on all fixtures, whether automated or not, is we want to internally plumb the hydraulic air and coolant lines. What that means is there's no plumbing. It's all gun drilled. We don't want to see any piping of any kind on fixtures, because anytime you have piping, it just attracts chips. They bird's nest on this plumbing. Not to mention, if you get a little too close with a tool, you could split a fitting open, you could split a line open and lose hydraulic pressure. So you won't see any of our fixtures with external air coolant lines or hydraulic. Through fixture coolant, we employ that to keep chips off the rest pads. We employ that to keep chips off the locating pins. We spray across the rest pads. We spray at the locating pins to make sure that we have chips removed. Designed for maximum chip flow, we want to make sure that the chips get off the fixture as efficiently as possible. And the last little thing I want to talk about, the fixture stocker wash. And what that is after the robot unloads the parts out of the fixture, the doors close on the front of the stocker stand, and we have vertical coolant pipes that have multiple nozzles in them, and we bathe that fixture in coolant. It just absolutely fills that whole area with coolant and just knocks any remaining chips off that fixture. Doors open back up again, the robot loads new parts onto a clean fixture. So we use stocker wash in combination with through fixture coolant to keep the fixtures clean. The use of automation is growing and into different applications. You need to try to understand the requirements and goals of the automation, kind of determine that, have an idea of where you want it to go. Evaluate the available types of automation to determine the best fit for the requirements. Evaluate the features of the proposed automation system, machining centers, and work holding systems as they pertain to the goals of automation. And if successfully implemented, sorry, I created a word there, machine utilizations of 80 to 95% are achievable, and our customers do see those type of utilization rates. All right, thanks, guys. I appreciate the
Yeah,
attention.
sorry.